All right, here we are ready to do the analysis. So this is the information that I had last time. 68.3 centimeters was the fall, and average time of 2.697. Assume I did that one correctly. Now, as we are doing the analysis, we have to first figure out what is the work done. Well, we have two masses here. Those are the masses. This was 210 gram mass, and this was a 200 gram mass. And they are connected by a pulley. And if we think about the forces acting on each of these objects, on this object right here, we have tension acting up, and we have its weight acting down. Call that mass 1, M1G. This one over here, we have tension acting up, and we have its weight acting down, M2G. Now, as we're trying to figure out the work done, remember that work is force times displacement. So this object is falling, and this object is rising. Now, if we think about this has two forces both doing work, this has two forces both doing work. Now, notice the work done by this right here, this tension, is going to be negative because this mass is falling and this tension is opposing it. It's in the opposite direction. This is in a presentation on work that I've posted. So as this object is falling, this tension right here is doing negative work. But this over here, on this other mass, the one that's going up, this tension is doing positive work. Well, if we think about that, I don't have to do the math on those, but this negative work done by this tension and the positive work done by this tension are going to cancel each other out. Because the tensions are the same. We do assume that the tension in the string was constant. And so since the tension in the string is constant, that means the magnitude of the forces are the same. And if the magnitude of the forces are the same and they go through the same displacement, except in opposite directions, basically they're going through the same distance, that the positive work and the negative work will be the same magnitude, and so they'll cancel out. So what I really care about are these right here, the forces done by the weight of each, or the work done by the weight of each object. And so the weight of this one right here is going to be the work done, M1 times G, that's the weight, times the distance that the thing falls. This one right here, it's going to be negative work, and so negative M2G times the displacement as this rises. This is negative here because the force is down, but the displacement is up. If the force opposes the motion, it's negative work. Over here, this is going to be positive work because the weight is down, the force is down, and the displacement is down. They're in the same direction, so it's positive work. And so I end up with this is the total work being done. The tensions canceled out. I worked through the argument. You can throw those terms in there, but they would just cancel out. And so let me factor out what I can. So I've got, this is the distance that I'm off screen there. So the work that's being done becomes, so the total work is equal to M1G times delta Y minus, and let me see if I can go for a darker pen here, minus M2G delta Y. And you're going to have to trust me that it says that. You might have a bit of glare right there. And so the total work is just equal to M1 minus M2 G delta Y. Now that's a little bit more math than you really need to know, but for some of you, it's the justification for what I'm doing here. Acceleration due to gravity is close enough to the same for both of them. Delta Y is the same for both of them. What I care about is basically what is the difference in the mass, which was 10 grams. So putting it into SI units, the work done in this case, so 0.01 kilograms times G, I think to the level of precision that we have here, 9.8 is sufficient. If you really want to do the math with a 9.796 for Winston-Salem, feel free to do that. There's 9.8 meters per second squared times how far the thing actually moved. What was delta Y? Well, that's right here. So 0.683 meters. That would be the work that's being done. And so now we bring out the calculator, and we end up with 0.01, enter, 9.8 times 0.683 times, and we end up with the total work that's been done is 0.0669 kilogram meter squared per second squared, or if we're dealing with work, I used SI, I know it's going to end up being joules. So 0.0669 joules. Now, according to the work energy theorem, that should be equal to the change in the kinetic energy. And so, next video, let's figure out what that one's going to be.